So now let's look at an improper integral that goes across the entire real line from negative infinity to infinity. Here's an example. So remember from our definition, what we did is we defined something like this to mean the sum of two improper integrals, where we divide this integral up into two integrals, stopping anywhere we like. Typically 0 is a good place because it's an easy number, it's right in the middle. So the idea is we're going to break this integral up and think of two pieces, the one from negative infinity up to 0 and the one from 0 to infinity. So our first step is to not really make it proper, but make it two improper integrals. Okay, now that we've done that, now let's make those integrals there proper. We've looked at both these types of examples. So first one, we want to approach negative infinity on the bottom there. A up to 0 of our integral. And then add to that this one we'll make proper by taking the limit as b goes to positive infinity. All right, now we're ready. We've got both integrals. Everything's proper. And so now we can evaluate the integral. Remember, 1 over 1 plus x squared. We know that from Calc 1. That's the derivative of tan inverse. So in both those integrals, the antiderivative is tan inverse. So we're looking at the limit as a approaches negative infinity, tan inverse evaluated at 0 minus tan inverse evaluated at a. And then we're going to add to that the limit as b goes to positive infinity of tan inverse b minus tan inverse 0. Now, these limits, tan inverse at infinity and minus infinity, we like to use tan inverse a lot as examples in here because it's a nice function as far as its behavior out at infinity. So let's remind ourselves what tan inverse looks like. Remember, tangent has asymptotes every time. Tangent's sine over cosine. So every time cosine's 0, you get that vertical asymptote. And in order to invert it, we made it invertible by taking only that one segment in the middle from negative pi over 2 to pi over 2. So when we invert it, those vertical asymptotes became horizontal asymptotes. This is pi over 2 and negative pi over 2. Tan inverse looks like that. And you can see why we like this as an example, because it's interesting in that whether you're going to positive or negative infinity, the limit exists. And it's an interesting number. It's not just 0. A lot of our limits are 0. And so it's kind of nice. And they're different. It's going someplace different on both ends. So going back to our limits here, what are we trying to do here? We're trying to go to negative infinity. So that's negative pi over 2. Tan inverse of 0 is 0. So we have 0 minus negative pi over 2. Over here, we're going to positive infinity, so we're heading to pi over 2 minus tan inverse of 0 is 0. So what we found actually is that this guy is pi over 2. And we could even see this by symmetry, right? This is a symmetric, even, it's an even function, so it makes sense that that side is pi over 2 as well. So altogether, it's pi. Now, a quick note about this definition. This integral is the sum of these two integrals. So if one of these integrals doesn't exist, if it's divergent, if the limit doesn't exist, then you don't even have to bother with the other integral, because if one of these diverges, we don't consider it, the integral is divergent. So if we had evaluated this piece and this had come out divergent, we don't even care what that second half is. The whole thing is divergent. There's no canceling of infinities. If this side's positive infinity and this side's negative infinity, those two chunks don't cancel. We'll look at an example of that in just a second. But this one does exist. Both that integral exists. It's convergent. We have a convergent integral here, pi over 2. We have a convergent integral here, pi over 2. And so together, pi. So this is a convergent integral overall from negative infinity to infinity.